Hello, my name is Desheng Zhang. In this short video, I summarize my research about data-driven cyber-physical systems and the Internet of Things for smart cities. If you're interested, you should feel free to send me an email and check my homepage for details. In a nutshell, my research is to analyze multi-source data from a physical urban system to infer urban phenomena, and then design and deploy practical applications to improve urban efficiency from an interdisciplinary perspective. My research is highlighted with 11 first author papers in premium computer science conferences. Those results are based on more than 10 TB physical urban system data across 3 continents. More importantly, I have been designing several real-world services, such as the bus arrival prediction in the Chinese city Shenzhen, used by more than 100,000 users every day. Based on my research, I have been honored with a few best paper, thesis, and poster awards and fellowships. Under Smart Cities initiative from the White House, I have been studying several big urban systems and their data around the world. For example, in the Chinese city Shenzhen, the urban data I personally studied include taxi, bus, subway, truck, smart car, and cell phone data from more than 500,000 vehicles and 6 million of smart cars and cell phones. Based on those systems and data, my research spans 3 key components of cyber-physical system. For the communication part, I design protocols for faster and efficient data collection. For the computation part, I analyze the collected data to design generic models to measure the urban phenomena such as human mobility and traffic speed. For the control part, I design advanced applications such as ride sharing and navigation to provide positive feedback to the urban system themselves. The major contribution of our urban phenomena modeling is a human mobility model based on incomplete yet complementary multi-source data. The existing work mostly models urban mobility based on biased single-source data, which leads to overfitting. In contrast, we propose a human mobility model based on multi-source data with a new model integration technique called multi-view bounding. It quantifies the bias of individual single-source data-driven models for context-aware model integration. Based on a combination of urban phenomena models, another major contribution of my work is a mobility-driven ride-sharing application. I formulate a non-linear optimization problem for the ride-sharing based on an overall mobility model, an individual demand model, and a collective supply model. I implement this service with 3 components: passenger client, cloud server, and onboard devices. I evaluate our ride sharing with a regional field study, a urban scale evaluation, and a national scale evaluation. I also verify the generalization of our model and applications based on the vehicle networks from 6 cities around the world. In short, the big picture behind my work is capturing urban phenomena by multi-source urban data from physical urban systems, and then formulate non-linear optimization problems based on a combination of those models in order to design practical applications to improve the physical system themselves. My research has several broader impacts, including funding proposals and course material based on my research result. I was invited for several talks at different places, and most importantly, I convinced our collaborator to release the first heterogeneous urban dataset for the benefit of the research community. My research also has several real-world impacts. I'm working with our collaborator in Shenzhen to design a bus arrival prediction system, which is currently used by more than 100,000 users. I'm also working with our collaborator in Dallas for ride-sharing implementation in their taxi and limo systems. And finally, I'm working with our DOT collaborators in Washington, D.C. for their bike system rebalancing. In short, my future work is to design and deploy practical applications based on heterogeneous model from imperfect data. 3 technical directions include imperfect data inference by tensor decomposition-based data fusion, heterogeneous model integration by CM-supervised multi-view learning, and feedback-based application design by robust model predictive control. Thank you for watching this video, and please send me an email or check my homepage for details if you are interested in my research.